Start recording. Side floating. Okay. All right, good morning, everyone. So within this semester, I think we witnessed summer, winter, spring, autumn, all of them within 3 months. It's amazing here in Georgia. But I like it. I like it. Okay, so welcome to the lecture number 15. Time is moving very fast. Today we'll talk about pre-alignment filtering. We'll continue with the next part. So last time we discussed the sneaky snake. We had some issue with the internet, so we'll try to cover the results again at the end of this lecture. But before jumping into the lecture, this quick announcement. We have assignment number 3 already released on iCollege. Please pay attention to that. We have a bit tight deadline this time, so please try to do it within a week. We'll try to move quickly with assignment number 3 and jump into assignment number 4. However, they are tightly coupled. If you do assignment number 3, it's really easy to do assignment number 4, which will be on optimizing the dynamic programming table. Assignment number 3, it's a bit straightforward, but requires some innovation in terms of detecting which subsequence exactly in the reference genome should be compared with the read. And we emphasize this a lot, many times. If you have a read short sequence, you have a large genome, want to extract the subsequence out of the long genome and compare only this subsequence with that read, so that we can do the dynamic programming table. We'll have this guy over here, and we have the subsequence over here, and then we start doing the comparison. This is always tricky, and that is actually the main contribution of any read mapper on how to detect this correctly and with high precision and quickly. We don't want to spend too much time on relating all the detected seeds. I give you some small hint, but it's up to you. If you don't want to use that hint, it's up to you. There's also an example on how detecting that. That's included already in assignment number 3. So if you are lazy, you want something ready, you can go ahead with the hint. You have some creativity, so I would recommend you finding your own algorithm to detect that. We have the dummy data already, so it will help you to verify the correctness of your algorithm. Want to see how the output should look like. So you already have the dummy data. And we already explained in one of the lectures what is the correct results. So we have in the dummy data 2 files, one of them FASTQ. And we have the FASTA file, right? We have here about 4 or 5 reads. We have here about very short genome, which is about, I think, 1,000 character or so. And in one of the lectures, we already show where are the correct mapping of each of the read. It was highlighted in a notepad file, if you remember. So you could use that as a ground truth, but it's up to you. You can verify it in your own input data. The TA will have another 2 files, so he can use it to challenge your algorithm. We don't want you to hard code the actual result. We don't want that. It's easy to work on the 2 files and say, okay, the correct result is at this location, so I want to hard code that number and always produce the same location. We don't want that, right? So we want any files, any 2 files, your algorithm should work correctly and precisely. Okay, as I said, the deadline 7 days. I think it's doable. Okay, but the hard deadline, it's 2 weeks once we have assignment number 4. So you could delay assignment number 3 and submit 3 and 4 together, but I wouldn't recommend that. The more you delay, the more pressure you will have. Okay. All right. So continue with pre-alignment filtering, and we agreed that we have indexing, seeding, and then sequence alignment, and that step is optional. And the main goal of this step only to improve the performance of sequence alignment. If sequence alignment was fast, we really don't need that step. So we could quickly perform this step and generate the edit distance or the cigar string and so on. However, until today, we have sequence alignment as a very expensive step, and our goal is to optimize it. And one way to optimize it, we discuss a lot on how to reduce the number of dynamic programming cells. But there is another way, is to reduce the need for dynamic programming in first place. So you could reduce the number of calculated cells over here, but most of the time, those two sequences that we are trying to compare with are really highly dissimilar. So we don't need to perform that because it will be useless. We just arrive until this cell, we find out the edit distance is 10, and our threshold is 5. So this is way larger than what we have in 5. And then we just trash all those calculations. We don't need them. So we discussed last time one way to do that is to differentiate between similar strings and dissimilar strings. And we said that the dissimilar string, those that do not share similarity, or the similarity between them is exceeding an edit distance threshold. So if they far exceed the edit distance threshold, then we call them dissimilar. And again, dissimilarity is subjective. So they could really be very similar in the beginning, like this entire subsequences are really similar, exactly the same. However, we start to see some variation over here. If this variation exceeding the threshold, done, we call it dissimilar. Okay. However, it could be also similar, which is less than or equal the edit distance threshold, and that would call it similar string. As we said just now, this will be an expensive scenario because we build the entire dynamic programming table, but then we trash it. So we lose all the computation we did over there. So pre-alignment filtering, try to focus on this area. Not in here. We don't talk about similar string. We talk about dissimilar string. So we want to detect those strings that are dissimilar from each other based on the threshold that we use. And if we detect them, done. We don't move to dynamic programming algorithm. Last time we went over sneaky snake. Hopefully you remember the algorithm. This time we will go over two more algorithms. The first one, called Magnet, was published in 2017. And just to recall what we discussed about the effect of edit operation, we have Atlanta and Atlanta as the two words. When I compare them together, so if they are perfectly exactly the same, then we have perfect match. So every pairwise character looks exactly the same. Now, if we do a single operation, just like deletion for the A over here, then since we delete that character, so all those trailing characters will be shifted to the left to replace that deleted character. And then the comparison will also be shifted. And without shifting that operation, we will have wrong matching. So we have A and N and T, T and A, which is wrong, right? So we have really to shift all the comparison operation in order to capture the similarity between the two strings. Likewise, with the addition, assume whatever character you want to add over here. So we are pushing all the trailing characters to the other side. And then similarly, we want to shift the comparison operation in order to capture the correct edit distance. Given that insight, so most of the pre-alignment filtering relying on this information, how we can shift the string correctly in one direction, either right or left, and then do the comparison to infer whether the number of edit operation or the approximated. We always emphasize approximated because sometimes we get it wrong, not necessarily to be correct. In a sense, if we predict it to be 10 and the edit distance 3, it's hard to predict it as 2, for example. Okay? Sometimes it's okay if we predict as 10 or 11, it doesn't matter. As long as it exceeds the edit distance threshold, then that's fine. There's no issue with that, even if we predict it as 20. As long as the correct one and the approximated one, both of them agree that it exceeds the edit distance threshold, we don't care. That's why we call it approximated edit distance. And it's up to you to develop your own algorithm, but you have to pay attention to that. However, if the ground truth or the correct edit distance based on dynamic programming algorithm calculated the edit distance as 2, for example, and the threshold as 3, but your pre-alignment filter calculated as 5, that is something very risky. Because the ground truth says it's less than the edit distance threshold, but you are saying it's exceeding the edit distance threshold. And this would result in deleting those sequence pairs, ignoring them. They will not appear in your result, okay? And that is very risky. So you have to pay attention to this, okay? That's why we keep emphasizing that pre-alignment filtering generate approximated edit distance, okay? And the approximation in this sense. If the ground truth is 10 and your pre-alignment filtering is predicting it as 5, will we have any issue? No, right? So if the ground truth is 10 and we predict it as 5, no issue, right? Because both of them still exceeding the edit distance threshold. However, if it is 10, the ground truth, and we predict it as 2, do we have any issue? The edit distance threshold is 3. We predict it as 2, which is less than the edit distance threshold. If it is less than, then we recognize it as similar string. Will we have any issue? Which is? Excellent. So we are going to calculate the dynamic programming algorithm, right? And we are going to figure out that we have 10 edit distance threshold, or sorry, edit distance value. We'll have it as 10 because this is perfect. And edit distance algorithm always calculate the right edit distance value. So we calculate as 10, but the pre-alignment filter says it's 2. And then this results in trashing the result after we calculate it. And we call this case as false. Exactly. Excellent. So we call it as false positive because positive, it means we pass it. It's positive because the pre-alignment filter says it's correct one. So we pass it. That's why we call it positive. And it's false because the next step, edit distance, going to trash it. That's why we call it false positive, okay? From the point of view of the pre-alignment filter. And that result in wasting some execution time. So the less false positive we have, the more or the faster your algorithm will be. So you have to pay attention to that in assignment number 3. That's why I said it's very risky or very tricky on how to detect that subsequence out of the very long genome where this read should be compared with. Okay? Yes. Yeah. So it's the same term. Sometimes it's tricky to call it false positive. So we call it false or falsely accepted or wrongly accepted. So you have a lot of terms to represent whatever happening here. The thing you should be clear that is it's wrong first. Second, it passes the filter, right? The filter didn't reject it, and that is wrong because it should be rejected. The later step will reject it anyway, so you should reject it earlier. And any of those terms should represent that, okay? But we don't want the opposite scenario. So vice versa, we don't want that. For example, if your filter, if it is 2, the ground truth, and you're saying it's 20, that would result in false negative, okay? False negative. Negative because the filter is going to reject it, and false because it's wrong. It shouldn't reject it. It should pass to the edit distance algorithm. Hopefully we emphasize that many times, so hopefully it's clear to you. So now let's go over magnet algorithm. The first thing magnet does is that we build a number of masks. Those are binary masks, and their number is 2e plus 1. If you remember, we have the exact same number in Sneaky Snake, right? So we have a matrix in Sneaky Snake. The length is the width or the height of the matrix is 2e plus 1, and the width is m, which is the length of the sequence, right? We have something similar here, but different way of how you calculate those masks, okay? First of all, the first one, we call it Hamming mask because it represents the direct comparison between the two sequences. Just do XOR operation between the two sequences. Hopefully, you are clear with XOR term. You know the XOR operation, digital design? If you don't know it, it's just a comparison, direct comparison between the character. If it is a match, then 0. If not a match, then 1. So if those two characters do not match, then we have 1s, okay? If they exactly matching each other, then we have 0s. That's it, as simple as that. That is for the first mask. For now, those set of masks, which we call them n deletion mask, and n is the shifted value. So we shift the query over one step in one direction, and then we do the comparison. So we shift the query by one character, and then we compare it with that sequence. And then we shift by 2 steps, and then do the comparison with the reference. We shift by 3 steps the query, and then we do the comparison with the reference. In the insertion, we do the shift in the other direction. If we shift to the right in the deletion, then here we will shift to the left. So we shift this by 1 step, and then we do the comparison in a sense that we are going So if when I shift and do the comparison, we would compare this with this with that, and so on, okay? This is how we do the shift operation and do the comparison. So we do A with A, ignoring this A, the first one, do the comparison this way, and then if we want to shift by 2 steps, we would compare with the corresponding third character. And that would be 2-step or 2 insertion mask, okay? And so on. Now, once we calculate all those masks, what we'll be doing, this is the correct result that you would get from Needleman Wunsch. That is after backtracking. So you got the cigar string, and those vertical bars represent exact match. So once you see those vertical bars, you know that is exactly match. So you have how many of those subsegments or segments? 1, 2, 3, 4. So you have 4 large segments as exact match between the 2 sequences. However, you can see some dashes somewhere. For example, here, you have 1 dash over here, have another, and you have over there. And those dashes represent edit operation, right? So either insertion or deletion. So over here, we call it as insertion over here, but deletion over there, insertion over there, which is C, but deleted from here, over here deleted, but over here as insertion. It depends on which one you're looking for. If you are looking at the reference, then we call this as insertion, deletion, insertion. But if you look at the query, then we call it deletion, insertion, and a deletion one, okay? Now that is the correct result, okay? And we are trying here to come up with an algorithm that convert those masks into this result. So your goal, you know this is very expensive, so we want to try to find alternative. And in Magnet, they come up with a way to generate those masks, okay? But now their goal, how to quickly find those segments which could be scattered around the mask. So in here, it was easy because scattered over only 2 masks, but those segments could be anywhere. So it could be here, here, and so on. So now the goal, how we could capture them much faster than what we have in dynamic programming algorithm. So now you may have some issues or some challenges in capturing those zeros. One idea was to do just AND operation. AND operation. You know, in AND, if you have 0 and 1, the result is always 0. Okay? 0 will dominate all the time. This is logic gates, right? This is how the computer operates. Just use logic gates. Does not understand analog or other complex operation. Now, if we have 0 and 0, so basically 0 and anything is always 0, because 0 will dominate. Okay? We have 1 and 1. 1, since we don't have 0, so 0 won't dominate. And 1 and 0, we have 0 again, so it will dominate, so we'll always have a 0. Right? So one easy way, one very fast way to do it is just to AND vertically all those bits together, right? We have 0, the result is 0, 0, 0, 0, 0. So the entire mask over here would result in a bunch of zeros over here, right? Because we have zeros, and those will dominate if we do vertically, regardless of this number. So it doesn't matter if it is even or odd. Now we have those zeros, again, would result in this segment. Those zeros would result in this segment. Those 0 would result in that segment. That was one of the ideas to do it, and we call this algorithm as gatekeeper, which we are not going to cover it in this lecture, but feel free to search for this paper called Gatekeeper, where we do AND operation between those segments. Okay. Now we have some challenges in doing so. If we want to do AND operation between all those masks, we have 4 issues or challenges. The first ones, since we do the shift over here, so we compare A and A as first character, right? But we don't have here anything to be compared with, then we are going to pad those masks with zeros. So we're going to pad here single 0, since we did only single shift, 2 zeros, since we do 2 shift operation, 3 zeros. And likewise over here, because now the comparison in this direction, so this character won't be compared with anything, then we will have single 0, 2 0, 3 zeros, right? So those going to always dominate, although we pad them, right, ourselves. So those artificial are not part of the alignment. And anything over here, those zeros will always dominate, causing a false positive. The second thing is that if we have any zeros anywhere, although they are not part of the correct answer, again, this is Needleman-Wunsch, so this is the ground truth. This is what we are looking for. This is for different sequences, so you would see the result here is different because those 2 are different from the previous example. Okay, but the goal here is to show if we want to do AND operation here, and the correct result here show as a mismatch. So we have a T matching with C. That's why we have a space over here. We don't have dash because it's not insertion, not deletion, it's just substitution, right? However, by some chance, by random, we got some zeros overlapping with that single 1. The correct result over here should have that 1. So we should have a 1 over here and all of those zeros and zeros. But if we want to do AND operation over here, those zeros are going to cancel the 1 over here, right? Because always dominate. 0 and anything going to result in 0. So that is the second challenge, how we could handle that. Now the third one, we have here, we have T and C, we have C and G, we have T and A, and those are 3 mismatches. However, in the gatekeeper algorithm, whenever we have consecutive 1s, we consider them into another number. So we don't consider them as 3 1s, as 3 edit operation. We have a reason why we do that in gatekeeper, but since we are not covering gatekeeper, so let's forget this slide, okay? However, the idea is just that we underestimate the number of ones, the number of edit operation. And that's a third challenge if we want to do the AND operation. Now, the fourth challenge, the edit distance operation, this is the result. And sometimes you have the zeros scattered over multiple vectors over here. So you can see segment of 0, another segment, another segment. And if we don't have 1 between the two segments, once we do the AND operation, those two segments will be merged together. You can see there is no 1 splitting those two segments, and that is resulting in, instead of the two segments over here, we're going to have here a 0 that result in having underestimation for this operation, which is a deleted character over there. Okay. So apparently, doing AND operation between those operation. By the way, the choice of AND was because doing so is very fast. You could do it very quickly in modern computers because you have the SIMD operation, and we talk about it in the early lectures, which is single instruction, multiple data. So you could perform the exact same operation on many data at the same clock cycle of the CPU, right? So doing AND operation for all of those numbers is not a problem. You could do it really quickly, okay? And it makes sense to use AND. However, we have all of those challenges that we discussed if we want to do AND for all of those masks all together. Now, how we could improve all of those issues that we discussed. So in Magnet, we provide an accurate analysis, all of those issues, and we show the problem with those issues in detail. So if you're interested, you can go read Magnet. You will see a lot of examples on those and what kind of issues those would result in. Now let's go into the detail of Magnet algorithm itself. I'm not sure if we should have this down. Maybe we could have it for now. Let's see. How many times we need to try? Yeah, sometimes it works after 3 times, sometimes more. Okay, anyway, it doesn't want more. Halfway. Okay, it's better to have it up. All right. Yeah. So the key observation over here that the correct alignment always includes the non-overlapping long identical subsequences. And those, we mean those highlighted in green color. So the correct alignment over here, it's always considering those highlighted as zeros, which are the long matches scattered over the mask. So why we always consider the zeros instead of the 1? Because the 0 represent an exact match between the character. And we should be looking really for those long matches of zeros. Please pay attention to this because this would be assignment number 4. So you're going to implement a pre-alignment filter on your own. So it's up to you to choose one of those we covered in the lecture or something else. Okay? So the key idea is to count the consecutive zeros in each mask and select the longest in a divide and conquer approach. So instead of doing AND operation, because it's going to result in some issues, part of them we discussed right now, we don't want to do the AND operation between the masks. What we want to do is first divide and conquer approach. If you remember, what is divide and conquer? It's a way or a technique to divide the large problem into smaller sub-problems, right? If we have one big problem, divide it into 2 sub-problems, solve each separately, and then merge the solution to find the answer for the whole problem. If the sub-problem is still large, you can keep dividing it into more sub-problems until this is naive to be solved. finding the smallest subproblem size you could find, solve that, keep merging the answer until you find the answer or the solution for the larger problem. And this is exactly what we are going to do. So the first step, we consider all masks, okay? Now just count what is the largest number of consecutive zeros in any mask, okay? This is one mask. What is the largest number of consecutive zeros? Let's see. Yeah, we have here a bunch of zeros. 1, 2, 4. We have 4 zeros. Here 3. We have over here 1, 2, 3, 4, 5, 6. So we have 6 zeros in the first mask. Okay. How about the second? Single, single, single. 2 zeros, 2 zeros. Single, 2, 3, 2, 3, 2, 1, 1, 2. Then we have 1, 2, 3, 4, 5. We have 1, 2, 3, 4, 5, 6. We have 6 zeros over here, okay? This entire thing. Or we have 3 over here. So we have 6. We have 6. Over here we have 2, 1, 2, 1, 1, 1, 1. We have, I don't know, maybe 160 zeros or so. 0, 2 zeros, and so on. We keep doing that, and we require those zeros to be consecutive. Why we require that? Because we want to find the long segments of matches. And we always have that observation that the correct answer coming from Needleman-Wunsch is just segments of zeros or segment of matches divided by edit operation, right? That's why we are looking for the consecutive zeros. Now, once we find the largest among all the masks, so out of here we find 6 zeros, here we find 6 zeros, here we find maybe 60 zeros, here maybe 1, and here 20, and so on. Now we have a bunch of numbers. We want to take the max out of all those numbers. So apparently, what is the max out of all number of zeros? Here we have 6, 6, here 60, 20, here maybe 6, 6, 6, 6, and so on. So the largest should be the 61 over here, right? That is the largest number. And what we would do, consider this as a subproblem and everything else as another subproblem. For example, this is subproblem, okay? This is another subproblem, the entire thing, and this as subproblem, all right? Now this is done, this is solved, because we already know that this entire segment is part of the solution since it's the largest, okay? The largest span of the entire thing. And that is one subproblem that is already solved. So we have 60 zeros, we move it into the answer over here. That is the answer generated by magnet, not the edit distance solution, okay? So this problem is already solved. Now we got 2 more subproblems. But before we move into subproblem, since we find one subproblem, what we are going to do is to skip one column and skip one column over there. Why we skip those columns? Since we have a division between this subproblem and everything else, then it means there is an edit operation to the right, an edit operation to the left, causing that segment to not span the entire thing, right? If there was not an edit operation over here and over there, so we would expect those zeros to span the entire length over here. But the moment we start seeing one over here and one over there, preventing those zeros from spanning everything, it means there was an edit operation happening somewhere that caused this segment to be scattered around those multiple segments, right? And that's why we skip one column from the left, one column from the right, and then now we consider the other 2 subproblems that are not solved, okay? Now, we exclude this region from the solution because we already solved it, and we move all those zeros over here. We add the 1 here and the 1 over here, right? Now let's repeat the exact same algorithm on the right side and on the left side. So which one to solve first, it's up to you, it doesn't matter. Now those two subproblems are separate, so you solve them separately. For example, want to solve this first. So just count how many consecutive 0 now in this region and this region. Over here we have only 2 zeros. Over here we have 1, doesn't matter which one you choose as long as all of them still max. Here we have 2, we have also 2 here. We have 3 over here. Over here we have a bunch of them. We have 3 over here. We have 2 and 2, so still the same. 1 and 1, we have a bunch of them. And over here we have 2. Now, in the answer here, we could have 2, 3, here maybe 20. Here 3, 2, 1, 1 maybe, or 2 over here. Now, what is the max out of all of those? Is the 20, right? So we choose that as the solution or the answer for this subproblem because spanning the largest area over there. And then we copy all those zeros into here. But remember, even if we have a 0 here, you don't replace the 1 we added. Imagine this as 1 and 1 or 0, 0, 0. It doesn't matter because we should maintain the zeros extracted from that subproblem and the 1 extracted from skipping 1 column. So we'll have zeros and 1, and then whatever coming up from solving that subproblem, we should have it in the final answer. Okay. So if we have 20 zeros over here, we'll copy them over here, and we have those 20 zeros. Okay, and by that, we already solved this subproblem. And now the exact same way as we solve that subproblem, we exclude 1 column from right and 1 column from left if they exist. Over here, we don't have anything left to the left side, right? So we cannot exclude anything. Over here, we still have, I'm not sure if this is clear to you, over here, we have 1 and 1. So we are going to exclude that one. We are not going to exclude the one over here. So we exclude only single column, which is 1 from here. Here we don't have anything, so we are not going to exclude anything. And then we add the 20 zeros. We add the single one only over here, and here remains as is. Okay. Likewise, if you want to solve this subproblem, as I said, doesn't matter which one you solve first. You want to solve the right or solve the left side. They are two separate subproblems. And that is the beauty of having divide and conquer approach. You make the problem really much smaller so that you can focus on each subproblem separately. Now, when you solve this, remember this, the yellow highlighted column is the excluded one from solving this subproblem. So what we have remaining is only this region. So over here we have 6, 3, 2, 1, 0, 1, 1, 1, 2, right? What is the maximum? Is it the 6? So we copy those 6 zeros into the result, and then we exclude 1 from left, 1 from right. Here, nothing to exclude. We copy that one to exclude it from the solution. Now what we have, those two subproblems, along with their excluded column, already solved, right? So we exclude 1 column. I think I skipped one transition. So the gray added here is the other two subproblems that we should solve. But you understand the idea, okay? So now this column is excluded, so don't pay attention to it. Now we have this subproblem remaining, and we have, this is excluded, so don't pay attention to it. And we have this subproblem remaining, right? So now we divide the problem to the right into two subproblems. One of them solved, which is to the left, this is the big one. And then we have one smaller remaining. The one to the right, we solve. The one to the right over there, the large box, and we have one more remaining. So this is solved. This is still not yet. This is not yet. This is solved. Now I want to solve these two, which is this little one and this 2 columns remaining. Now we repeat the exact same thing. Nothing changed. So count how many zeros in this column. We have single, zero, single, single, single. So just copy the 0 over here. And then we add 1 to the right, 1 to the left, which is already added from the previous iteration. So we don't add physically anything. We just keep that little 0 over here. And here we have 1, 2, 0, 0, 0, 1, 1, 1, 1, 1. So the largest would be the 2 zeros over here. Remember, this is excluded column, so we don't care about it. And we have 2 zeros, so we just add them here. We had 1 to the right, 1 to the left, and that's it. Okay? And that will be solving the entire thing using magnet. And you can imagine why we call it magnet, because we try to attract those zeros from the masks into that final bit vector, right? So we attract them. It's like a magnet, and we attract all those metal devices or zeros into the final bit vector. Now the total number of ones, let's have it clear. The total ones resulting from excluding columns from right and left in all of those segments, representing the edit or the approximated edit distance. Whatever we have as ones over here, it is the answer that we are looking for, which is the approximated edit distance. Okay, and then we compare it with the edit distance threshold. This is greater than a threshold, means this is a wrong, right? Just ignore it. We don't need to do the dynamic programming table. If it is less than or equal that threshold, then we should perform that operation. All right? Now, how many times we should have subproblems? Think about need to erase something. Maybe here. Now, if we are looking at the edit distance result, like Needleman watch, we have the cigar string. If we have one operation over here, meaning, for example, we got like 10M, 1D, and 20M, that means 10 matches, 1 deletion, 20 matches, right? Although sometimes it's tricky to represent M in the cigar string. We discussed that M is not necessarily a match, right? It could be a mismatch too. You remember this from the cigar string. So we have the M over here could be a match, or it could be a substitution or a mismatch, right? But let's consider in this example as a match. And we have one edit operation. How many subproblems magnet would result in? Excellent. So we have this entire alignment split it into 2 long matches or 2 long segments of zeros, consecutive zeros. So we have a lot of zeros, right? And a lot of zeros. We detect those, or we count those number of zeros first, and that is the first subproblem. And then the entire problem would be divided into this subproblem and that subproblem. We solve this first, assuming this is the largest number, or sorry, this is the largest because this is 20 zeros and this is 10 zeros, right? So we'd solve this subproblem first, and then we have this as remaining subproblem, we solve it, and then we got the result, right? Okay, that is the result of single edit operation. Now if we have the cigar string as this, we have matches, edit, matches, edit, and matches. What will happen? How many subproblems will have? 3, right? So assuming this is 10 matches, 30, this is 8. What will happen? Magnet will detect this first, right? This is the longest number of zeros in one segment. and then exclude column from here, column from there, and then detect this sub-problem separately, solve this. This will be solved first, this is second, and that is third, right? And then we have 3 sub-problems. And then the number of iteration over here, apparently it's related to the edit distance that we have, right? So it's always E, which is, this is edit distance threshold, uppercase. We said the lowercase is the edit distance value, the actual value, not the threshold, but the actual value. Here we have 2, so it's E plus 1. That would be the number of iteration that we should maintain in magnet, how many sub-problems. And this would give you directly the depth of the tree. So how many levels we should go with the tree in order to solve this, okay? And that gives you some sense out of the complexity of the magnet algorithm. So basically, whenever we have edit operation, it's going to split the correct alignment or the correct edit or the correct cigar into E plus 1 segments. So if we have 3 over here, we'll always have 4 segments of zeros. And that would be the answer to the problem. Now, we have some details about how we could implement this in hardware. What is the complexity needed? And this is the structure that we use to implement it on FPGA. How many of you know the FPGA? Field Programmable Gate Array, which is an array of gates. So this is a hardware device. This is like customized chip where you have inside the chip, this electronic chip. You have inside it an array of gates, array of gates. So you have a lot of logic gates over here, a lot of them, sometimes million of them, okay? And those gates could perform any of the operation that relate to the logic. We discussed AND operation, which is part of them, but we have many more operation. For example, OR, XOR, NOR, NOT, and so on, including the AND that we discussed. So this is really the computer. What we have in the computer, just gates, just logic operation, okay? This is how we can perform this operation. Of course, we have some other complex operation happening in the computer, but the digital computer or the FPGA normally consists of those gates. So if you want to implement something on this device, on this hardware, your algorithm should only rely on logic gates. Your algorithm should reuse one of these operations. You cannot use your own algorithm just as simple as that. Like you come up with the algorithm, try to implement it in the hardware, you either implement it in a wrong way, so you are losing the resources, you're not exploiting the full power of the FPGA, or it won't work, okay? So if you want to target this hardware, you have really to pay attention to the supported operation that you could use in the algorithm itself. We're not going to cover the hardware side of it. But as we said, the key idea of this algorithm, by the way, you could still implement the algorithm in a software. Have it as Python code, which it's up to you. In assignment number 4, you're going to choose the pre-alignment filter you like and implement it on your own, okay? There is no issue with implementing it in Python. As you can see, the operation over here, just simple for loop, right? You go over the mask, you count how many consecutive zeros, and you maintain a counter or a count for each of those masks, right? And then you could find the maximum, then you have that as solved problem, and then you have another for loop to iterate over this. Whenever we don't have it as zeros, it means we didn't solve that subproblem, right? So you could initialize this entire bit vector with ones, and whenever we have zeros, replacing the ones with 0, it means we solved that subproblem. So your for loop should keep iterating over that bit vector. Of we have all those zeros, then we shouldn't do anything in this region. So we should skip them from the for loop. And then the for loop would recognize those as ones because we didn't solve them yet. Then the for loop should iterate over this, try to find the maximum length, and solve that as subproblem, and so on. Likewise, in here, we will have a lot of ones because we initialize that bit vector with ones. Then we could solve this using the same for loop, and so on. Keep doing that iteratively. Okay? We have some results for magnet. It's up to you to check it. You can see it in the paper, but we are going to do the comparison with all the bit vector we will discuss today. So let's skip this, and we will revisit it again in the last slide. The source code of magnet, it's already public on GitHub, so you can play with it. Now let's do something else. Now apparently, what we would do over here is for loop for the entire mask. The for loop will go over the entire mask, right? So we're going to count those zeros starting from the first character all the way to the last character. So we'll iterate over the entire thing first, try to find the first subproblem, and then iterate over this subproblem only, and this subproblem only, and so on. So on average, we're going to go 2 times over the same mask, right? Because the first time, we go over the entire thing, trying to detect this large subproblem, right? We go from one character to all the way to the last to really find this region. And that will be one time we visit, right? The second time is the subproblems left or remaining from solving this subproblem, which is this entire thing, plus that thing. So the second time, so we have 1x, which is one time, plus 1x minus something, which is the subproblem that we solve over here. So in worst case, we're going to solve this entire problem 2 times. The first one is to recognize this subproblem. The second time is to solve the other remaining problem. Now, if this subproblem was small, then we are going to visit the entire thing again, over and over, right? And that giving us some complexity, which is related to what we call scalability. The scalability problem means if I change the sequence into longer sequence, what will happen to the problem? For example, if you have 100 character compared to other 100 character, now it's related to 2e plus 1, right? This is the number of masks you are going to build. So if e is 2, then we have 5 masks. So 5 times 100. So we'll have 1 mask, second, third, fourth, fifth, right? That will be the problem that we're going to solve using magnets. So we have 100 over here, we have 5 over here, right? Now, if I change that number from 100 to 1,000, we expect the problem to be 10x greater than the problem over here, right? Because we expand each of those masks by 10 times instead of 100 into 1,000. So does this scale going from 100 to 1,000? Now, million, same thing. You multiply by 1,000 and so on. This is not good scalability. This is not scaling well. Why? Because we just expand based on the input. If the input is increasing, the problem becoming bigger and bigger. And that is a great challenge for us because those are limited resources. It's not related to hardware, but also in software. If you want to implement it, your for loop size is going to increase as well. Instead of iterating from first character to 100 character, now you are iterating from 1 character into 1,000 characters. So your for loop also increasing. And whenever we have such thing, that is not good scalability, okay? A nice algorithm that's scaling well, if I have a problem of size 100, and if I have a problem of size 1,000, if I solve both of them in the exact same time, That is good scalability. Okay. So we had an idea on how you could do that. Which is the next paper that we are going to discuss. Called Shuji. Was published in 2019. This is the name of the paper. And we will see why we call it Shuji. As you can see from the writing over here, it's a Japanese name. Okay. All right, let's go to the example directly. So regardless of how we build this data structure, in Shuji, we need to have, similar to the dynamic programming table, okay, there are no masks over here. We have a dynamic programming table, we have a sequence and another sequence. And whenever it's matching any corresponding character, we just place this star, okay? Or could be 0, could be 1, could be anything, representing an exact match between the corresponding character. And this is similar to what we discussed before called dot plot. Do you remember? This is what we discussed in one of the lectures. Whenever you have a dynamic programming table, any of the character is matching, you place something, right? This means the character over here, the character over there is matching, right? And over here, the character over here and the character over there are matching exactly, right? So that is in a simple way of what is the data structure used for the Shuji algorithm. Now, what we want to do, or the key idea of the algorithm, is to use overlapping sliding window. Overlapping sliding window over that data structure in order to detect the long segments of consecutive zeros. Instead of having this entire data structure from magnet, you have all those masks, right? Instead of visiting the entire thing and try to find those long matches of 0, we're going to use an overlapping window. For example, this window, and then the next overlapping one, next overlapping. And that is how Shuji would work. Let's see an example. Always example, clearing all the confusion. This is some details about how to build the data structure. Please read it on your own, but you will see it in the next slide clearly. Okay, we have a simple equation over here. We already discussed similar equation in multiple occasions, so it's easy for you to interpret it. The cell in the dynamic programming table, let's not call it dynamic programming because there is no dynamic programming approach in this paper, okay? We can call it a table, for example, or a matrix. So a cell in that matrix, it's either 0 or 1, a binary 1, okay? 0 if the corresponding character are the same, 1 if they are not the same, okay? Now first you build it, you build that matrix. So again, as we discussed, any character equivalent to the corresponding character, we have a 0, otherwise 1. And if you use edit distance algorithm, you will see the solution, or the cigar string, consists of those zeros. So it means the solution is basically 0 from this column, 0, 0, 0, and then 1, and then 0, 0, 0, 0, then 1, 0, and then 1, 1. Because this is going to this cell and this cell. Okay. Now that is the correct answer coming from edit distance calculation. It means if I want to convert this into cigar string, I would say 4m, 4 matches, then 1 something, could be deletion or insertion. Let's have it as D, and then 4 more matches, 1 D, 1 M, and then 2 D or mismatch. Could be anything, right? Those mismatches. But this would be the cigar string. Now, yes. Because this would be the solution, right? How we arrive from 0 to here. So I made it up myself that the solution or the answer might be this way, right? But could be this way and then this way, right? But I assume it myself. Now it's highlighted in yellow. That would represent the correct answer, right? From edit distance operation. But I don't know what happened over the end. But apparently, we are 2 steps far from this corner. That's clear, right? There's no confusion about it. We are really 2 steps far from this one. So it's either this way, could be this way, and then this way, and then this way, could be this way, could be this way, and then this way, right? Which one has the minimum number of steps? Apparently is this and then this, right? Or this and this. But not this, of course, because this is 1, 2, 3. Then we have 3 variation, and you know edit distance is about the minimum number of edit operations. So we shouldn't go for 3 operations or 3 ones, right? So that is clear from this figure. But you already have the sequences over here, so you could do it on your own. You could calculate the edit distance between this and figure out the correct answer. But anyway, it's already highlighted to tell you that there are 4 exact matches. Let's see them: G and G, G and G, T and T, and G and G. That is perfect match, right? And then something happened after the 4th character. Something happened in here and in here. Here it's C, but here it's A. And we don't know this is happening because of insertion or deletion, then all the characters are shifted. But this is given to us now from Shuji. And Shuji is going to do a window, a sliding window of size 4. Okay, so we have 4 columns. 1, 2, 3, 4. 1, 2, 3, 4 columns. Okay, that will be our subproblem. We are going to focus on this subproblem separately from the entire thing. What we are going to do, going diagonally, counting number of zeros. We don't count here the consecutive zeros. We just count zeros, okay, regardless if they are consecutive or not. Diagonally, this shape, right? This anti-diagonal, we call it, right? And this is diagonal, okay? So here, diagonally, we go over those diagonals because we call this as main diagonal, right? Do you remember from edit distance operation? The one in the middle is the main diagonal. You have next to it and so on. So diagonally, how many zeros in each of those diagonals? Within the window only. So we only focus on those 4 columns. So here we find, I don't know, 1. Is it 1 or 0? Yeah, 1, 1, 1, 4, 1, 2, 1. We always go to the maximum number of zeros. Why is that? Because we observe that always edit distance operation or Needleman-Wunsch, Smith-Waterman, any of those operations will always have number of matches and then an edit operation, number of matches, edit, number of matches, edit, and so on, right? It's always happening like that. And those are the genetic variation causing the disease. And that's what we are looking for. So we always look for maximizing the number of matches as much as possible. In a sense, once we find all those segments, we will find those variations, right? It's the opposite way. Our goal is to find the mismatches, right? But as a proxy or as a workaround, we're trying to find those instead of those. We're trying to find the long matches or the long zeros, the long segments of zeros. And once we find them, the remaining are the matches themselves, right? This is one way to look into it. But in edit distance operation, we don't know those in advance in the dynamic programming. So we build the entire thing, and the last cell will tell you those edit operation, right? So we don't have an answer to find those. We just try to find those using the dynamic programming algorithm. In a pre-alignment filter, we always look for those long matches of zeros, hoping that once we find all of them, the remaining vacant places are the edit operation that we are looking for. And that is our ultimate goal, is to find those genetic variation between two sequences. That's why we are looking for the largest number of zeros, although in this algorithm, we don't consider the consecutive zeros. But anyway, they will be consecutive, right? Anyway, they will be consecutive. Because here, all of them are next to each other, the zeros. So even if we consider 4 characters at the time, at any given time, the answer would be all those zeros next to each other, except, of course, once we visit this area. We will have some problem over here. So in here, as you can see, the highlighted yellow cells are part of the correct answer because those 4 characters are exactly matching with those 4 characters. That's why we have 4 zeros next to each other. And then the Shuji algorithm would predict the number of matches correctly within that window. Now, once we figure out that we have 4 zeros, we copy the solution somewhere else as auxiliary data structure or auxiliary array where we maintain those matches. Okay. Now, since this is overlapping window, so we shifted by 1 character, and now we consider the next 4 columns, starting from here, 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 here. Now we have, this is 1, 2, 3, and 4. Okay. Now we keep doing that for each of those diagonal. How many zeros? 1, 1, 1, 1, 1, 3, 0, 2, 1. Now we are somewhere around or close to the edit operation over here, which is the tricky part. So we already span some of those matches plus the mismatch itself. And that is the tricky part. So you can see here, this is the correct answer. Now we exceed the correct answer, we move to somewhere here. That caused this correct answer to be splitted from this correct answer. We find it as 3, and now we want to consider this over here. So this sliding window, the previous sliding window resulted in 4, 0. The next sliding window would result in 0, 0, 0, 1, right? Because this is the largest number of zeros, which is 0, 0, 0, and this is the next one is 1. So now we don't have any issue with having 2 solutions or 2 answers overlapping to each other, because this and this and this agree with this and this and that, right? So we could just merge the 2 solutions together, and we have it as that, okay? Now, apparently, you can see we gradually build the solution by having a fixed subproblem, fixed size subproblem, which is 4 columns every time. We could solve that and merge the solution over here. Now, let's see the third sliding window. The third sliding window would be from here. Maybe we can have it in red color. Let's clear this first. Now, what we would have, this is the limit, maybe more than this. Over here, we don't have anything, so 0. Over here, we have 1, 0. Over here, 1, 2, 3, so we have 1, 0 as well. Over here, we have 0, 1, 1, 1. So we have 1, 0. Over here, we have, oh, sorry, I'm counting in this window. This is the old one. So we have here nothing. We have 1, 0. We have 1, 0. Over here, 1, 1, 1, 0. So I have 1, correct, okay. Now we have in here, did we skip this? Oh, we have 2, correct. Yeah, so we have 1, this is the first, second, third, fourth, so 2. Now we have here 1, 1, 1, 0, which is 1. And then 1, 0, 1, 1, which which is 1 again. You have 1, 1, 1, 1, 0. And all of those are 0, nothing. Okay? So we are going to go with the 2, which is 0, 0, 1, 1. So we have, this is already computed. So we have at this column, right? Yeah. Have 0, 0, 1, 1. Okay? And that will be the merged answer. Remember, this is coming from the first problem. This is second problem. And this is the third. This is the third. Okay? Up to here. Now, as you can see, there are zeros coming from here, which is coming from the next problem. Because every time we got a subproblem of size 4, we try to merge the solution. Okay? So the next subproblem would be apparently 0, 0, 0, because this is part of the answer. So we'll have here overlapping as 0, 0, 0. Now, from the previous subproblem, which is the third window, this one, we got 0, 0, 1, 1. But the next subproblem gives us 0, 0, 0, 0. Now, when we merge them, what we should do with the overlapping 1s and 0? Here we have only single character overlapping, this and that. Which one we should consider, the 1 or the 0? Remember, our goal is to maximize the number of 0 in here. Try to find the longest segment of zeros, right? This is our goal in pre-alignment filtering. So whatever solution we got from the subproblem that maximized the number of zeros, we will go for it. So if this subproblem giving us 4 matches, but this subproblem giving us only 2 matches, then we'll go with that solution. And that solution overlap with the previous solution with only single character, then we are going to cancel that, and we have the 0 from the next subproblem over here, 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 here. Now the next subproblem going to overlap with here, so those 3 bits could be replaced. But since they are zeros, this is always the best thing, to have zeros. Then we are going to maintain them, and so on. So every time we solve by subproblem, this is 4 columns, we always overlap with whatever result in here. This is going to maximize the number of zeros, we will replace that, okay? We will replace or overlap, overwrite the previous solution from the previous subproblem with the new result, and so on. Is it clear? Okay, so the best thing with this algorithm is that we have subproblems of fixed size, and always when we have a fixed size, that is always very good for the hardware as well as the software, because you already know in advance what is the subproblem. You already know in advance that the first subproblem is first column, second, third, fourth, and the second problem is second, third, fourth, fifth, right, and so on. And that is giving you a very good time designing the algorithm, because you already know in advance these subproblems always fixed, regardless the sequences. Even if I change those sequences, the subproblem would remain the same, right? Doesn't matter, doesn't rely on the sequences themselves. And that was different from magnet. So in magnet, we cannot know those subproblems in advance. We have to go over the entire mask, count the consecutive zeros, and then we could decide that this is the first subproblem, then we have 2 subproblems, and so on, right? But over here, you already know it in advance. The only thing that you cannot decide is how to merge the answer of all these subproblems together. So that is said in a sense that you could solve all those subproblems in parallel. You really don't need to wait for the second subproblem to be solved in order to solve the first. And you don't really need to wait for the first subproblem in order to solve the second. And likewise for the third, fourth, and fifth, right? So you could solve all of them, but only when you merge their answers, you have to wait for the first, and then second, third, fourth, fifth. So you could merge them all correctly in that bit vector. And this giving you a lot of parallelism. So if you have a parallel for loop that could iterate over all those subproblems. You could solve all of them in the same time and then just merge their answer. And this is very good for GPU, for example. GPU, you know, we have a lot of threads similar to the CPU. So we have a lot of threads that each thread could focus on one subproblem, right? And then once you have those subproblems already defined, so you can launch like thousands of those threads. Each of the threads will solve some of those problems, and then you just merge the answer to that and find quickly what would be the optimal number of ones or the approximated edit distance. Okay. Likewise with the FPGA, since this is a large array, like millions of those gates, so each of those subgroup of gates, you could dedicate for each of those subproblem, and then you could solve it quickly and in parallel. And this is what we talked about in terms of scalability. So this algorithm could scale very well regardless the number of characters in the two sequences. Because simply, you just solve all the subproblems in parallel. It doesn't matter if those subproblems are 100 or 1,000 or million, all of them will be solved in the same time. So when we talk about scaling the problem from 100 character to 1,000, it is still the same thing. Assuming, of course, you have the right hardware to operate on all those subproblems at the same time. And this is possible with even CPU, because you also have multi-threading in CPU, right? So you could use the same thing for multiple threads and try to solve something in common. Although sometimes the CPU here are limited with 8. They have scalability and granularity of 8, right? 8 threads. Sometimes you have more threads if you are operating in capable CPU, let's say, like 256 threads, 500 threads, and so on, especially if you are operating on server grade CPUs, right? So the number of approximated edit distance that we took over here is the number of ones. Here we have 1, 2, 3. So we missed the 2 ones over there, right? So Shuji, underestimate the 2 ones and have them as single one at the end result. And we always said underestimation is always fine. Would be considered as false positive. You remember what we wrote here? False positive. So having false positive is fine as long as we are doing this algorithm much quicker than what we have in dynamic programming. If we are very fast in deciding what is wrong, what is correct, and we don't have false negative, we are not rejecting any correct sequences, it should be always fine, okay? Yes. No, the size should remain the same, 4 columns. It's not changed. And that is the best thing about the algorithm. It's always 4, okay? Why is 4? We have one slide for that. The next 2 slides, we will see why we choose 4, not 5, not 6, not 3, right? But this always fixed size. If it is variable, we would be similar to magnet, which is not good, right? Very good question. Now, why we call it Shuji? I have one video. I think I'm done with explaining the algorithm, so I'll try to have this down. Bless you. Looks like sneezing will solve this problem. We always fix it if we sneeze. All right, so this video, my friend in Japan sent it to me. He's one of our collaborators. I visited him 1 week before COVID travel ban. So I visited him in December, and the COVID ban was applied, I think, around January or so. So let's watch it together. I'm sure you already see some of those doors, there's a sliding open door, very famous in Japan. Almost all houses, they have that door. And the name of this door is Shuji. And that is the name of the algorithm. So we call it Shuji because of that door. And why we call it this way? Because apparently you have that sliding window visiting the entire matrix that we built as zeros and ones, right? And the size of this door is 4 columns, and you're sliding over the entire matrix, right? And that was the reason behind the name. Right. Here we evaluate, what if we use a window of size 1? What if we use a window of size 2? What if we use window of size 3 and size 4 on the false accept rate, which is the false positive? We know that if our site is limited by this window, then we're going to see that much of exact matches, that much of zeros, right? We are basically limiting our site to be focusing on 4 columns or 4 zeros at the time. So the lower we limit the size of the window, then we are going to not see those long matches of zeros. Imagine if this, for example, if we go to magnet, it will be clear in one of those. Imagine our window size is 1. So in this column, are there zeros? Yes, we have a lot of zeros. Then we would have 0 here, right? The next window, do we have zeros? Yes. Do we have zeros? Yes. Do we have 0? It doesn't matter if it is coming from this or somewhere else, because everywhere we have zeros. You can see we have this as the correct answer, but we have also zeros scattered around here. And it's kind of impossible to not find a column with zeros, right? It doesn't matter if it's part of the correct answer or not. Even in here, which is supposed to be 1 based on the edit distance operation, even in here, you have zeros. So you would result here in 0, 0, 0, 0, 0. So at the end of the day, in Shuji, you will have the entire bit vector as zeros. And then we have 0 filtering. You're not going to filter anything. That is if the window size is 1. Now, if the window size is 2, somehow better, a little bit better than what we have in size 1. But you can see sometimes we have a lot of 2 zeros consecutive or next to each other. So here we have 2 zeros. Here, yeah, maybe we have 2 zeros over here. Here we have 2 zeros, 2 zeros. But also we have 2 zeros in here. Let's see this tricky region. We also have 2 zeros, right? So having 1 column and 2 column would result in having also too many 2 zeros next to each other, because this is normal. You can expect to have 2 zeros everywhere. You can see here we have 2 zeros. Over here we have a lot of zeros, so we still capture them. But over here, if you want to capture this one, we also have 2 overlapping zeros. So we're going to choose this in the sliding window. And that's going to give us a hard time on how we could capture the correct answer without overlapping the ones with 0. Remember, if we got a bit vector all full of zeros, we're not going to filter anything. We're going to accept all of them, because we don't have ones to count them for the approximated distance. And that will be the problem with having sliding window of size 1 and size 2. Okay, it's going to give us a lot of false positive. We're not going to get false negative. In a sense, we're not going to overestimate, but always underestimate the right number of edit distance, okay, or the approximated edit distance. That's why we have high rate of false positive. But once we move to 4, we notice that this is the right number. Now, what if we go to 5? What if we go to 6, 7, 8? We start see a false negative over there. Why is that? Because in some cases, I don't have the example, but you will see it in the paper. In some cases, when we go with 5, especially if there is 5 over here, 5 zeros, and we choose them, then we are going to overlap with the existing ones. And then, we're going to see a lot of ones that are going to overlap with the answer over here. And then sometimes going to overestimate rather than underestimate. And then we figure out that the size of 4 is the best to not have false negative, but also very low false positive. Okay? Now, there are some other details on the FPGA. What is the size for the lookup table or the number of gates that we should consider for each subproblem over here. We have a lot of optimization for the hardware. But since this course is not related to hardware, we're not going to discuss it in this course. We will keep focusing on algorithmic side. Now, let's skip the results because we are going to discuss them with overall result, which is related to Sneaky Snake. Once we skip, if you remember the previous lecture, we have the issue with the internet, and then the recording was disrupted. Maybe I can erase over here. Now let's discuss the result for all the pre-alignment filters all together, which is Sneaky Snake, Magnet, and Shuji all together. Let's see what is the best out of all those 3 alignment filters. All right. Do you remember Sneaky Snake algorithm, which was a maze, chip maze we built, and then we count from left side how many zeros we could move ahead, how many zeros, and then once this is the largest path, we go over it, we add 1 obstacle, and then we jump into next subproblem, right? We keep doing that. And this, apparently, as you can see, is the minimal data structure that we built out of the 3 algorithms, out of Sneaky Snake, Magnet, and Shuji. So in Magnet and Shuji, apparently you build the entire thing, the entire matrix. Either you build it horizontally as in Magnet, or in Shuji, you build those diagonals, right? But in Sneaky Snake, you barely build 1 row, 1 complete row, because part of the solution, sometimes like this, right? So you build this segment fully, this segment fully, this segment, plus some minimal number of subsequences over here. And that is the lowest number of cells that you're going to build. So this is going to impact the execution time of Sneaky Snake, positively, of course. So that's going to be the fastest pre-alignment filter. So it's up to 4 orders of magnitude more accurate first. And in accuracy, all of them are false negative, right? False negative of 0. And minimal false positive. Now we are talking in terms of accuracy about false positive, okay? Now the best algorithm that has the minimal false positive is Sneaky Snake. In terms of short sequences, when we talk about short, if you remember, Illumina, which is limited to up to 200, sometimes 300, that is what we call short read or short sequences. So Sneaky Snake still faster than even edit distance operation or algorithms, including edlib. So edlib is edit distance library. This is the fastest implementation of edit distance or Levenshtein distance that we discussed in the lecture. So if you want to get the best performing edit distance algorithm, you should use edlib. Okay, that's the best one currently. So Sneaky Snake is faster than that. So if you merge them together as a filter and as edit distance algorithm, you would get the best combination of those 2 algorithms. Okay. We also have some results on CPU, and FPGA, and GPU because Sneaky Snake we implemented on 3 platforms. One is CPU, The other is GPU and FPGA. So if you have access to any of those hardware, you could run Sneaky Snake directly. So we have one project for that, one for that, one for that in the same GitHub repo. Now, when we talk about long reads, which is something greater than the 300, we test up to 100,000 long sequences. So we use in this analysis KSW2. KSW2 is the sequence aligner, not edit distance. Okay, do you know the difference between sequence aligner and edit distance? What is the difference between edit distance and sequence alignment? We already discussed it in one of the lectures. It's related to customized penalty score, right? So the edit distance, or what we call Levenshtein distance, sometimes we call it unit distance, because all operations are penalized with 1. That's why we call it unit. Okay? All operations are penalized with 1. Doesn't matter if we have insertion, deletion, substitution, matches, all of them 1. Okay? Now in sequence alignment, if we have 2 alignments of the same edit distance, which one to choose? We have to favor one of them. Either we favor insertion over deletion or deletion over insertion. And that's why we have customized penalty. So we penalize the D with something, the I with something, and the substitution with something else, the matches with something else. Okay, and based on that, we could favor one edit distance value or cigar over another cigar. Okay. Now this is the accuracy. This is edit distance threshold, which is E, not uppercase E, not smaller case e. So this is a threshold, not the edit distance value. So if you set the threshold from 0 to 10, varies, like you sweep the value, then the false accept rate, which is something we want it to be minimal. Of course, we cannot have it as 0, cannot have 0 false positive, because otherwise it will be a perfect edit distance algorithm. Now we have here SSD, Gatekeeper, Shuji, Magnet, and Sneaky Snake. We have 2 configurations for Sneaky Snake, but forget about them. This is a detail you can find in the paper, but this is not the main point here. The main point is that somewhere when the edit distance value is low, like if you're interested in only no edit operation at all, or single edit, or 2 edits, or 3 edits, still all of them are performing very well. So all of them in terms of accuracy performing really well. Now, once you exceed the edit distance threshold, like you're interested in having 2 sequences with 6 edit operation at most, right? If you choose your edit distance threshold as 6, you start seeing the difference. So the green and the blue are SSD and Gatekeeper. The yellow is Shuji performance. The red is Sneaky Snake with one of the configuration. And the green and the black are Magnet and Sneaky Snake. So you can see, of course, the lowest is the best. Whatever closer to 0 is the best, because we will have minimal false positive. So whatever remain near the 0 is the black and the green, which are Magnet and Sneaky Snake. However, you can see Sneaky Snake always the best or the least false positive rate, regardless of the edit distance threshold. Okay? If you're interested in Shuji, for example, you can still get somehow acceptable performance, even with a high edit distance threshold. The red one, or the green, which is Magnet, you can get somewhere between Sneaky Snake and Shuji. So the decision for assignment number 4, it's up to you. You can see based on this figure, so you would expect how much you can slash the time or the execution time of edit distance. Assuming you use no edit distance, no pre-alignment filtering at all, which is assignment number 3, you're not going to use any pre-alignment filtering. You'll directly use edit distance algorithm. Let's see how much execution time you would get, right? And then in assignment number 4, you start using the filter. And then we would see if your execution time is going to increase, then the filter you use didn't do a good job, right? Because it's going to give you a lot of false positive. All the sequences coming to the filter will just pass. So it will be useless, but it will be a burden. Why? Because we calculate extra thing in filtering, right? So it will be a burden, and then it's going to slow down. And that thing we don't want it. So if you have gatekeeper, for example, you'll have 100% pass rate. So everything's going to pass, right? So if you use gatekeeper with edit distance threshold of 10, then you expect your execution time to go much higher than without pre-alignment filtering. So this figure is really important for you to decide which algorithm you should use, okay? And what you expect, either an increase in execution time or decrease. We have a lot of figures. We don't have time. So maybe we can cover this paper published in 2024 called KidZal. We got the best algorithm out of edit distance, which is wavefront. We discussed in the lecture. And we got the best pre-alignment filter algorithm. We can see the performance, the execution time of only the best edit distance threshold or sequence alignment compared to the speed up that we would get if we merge them together. Now this sneaky snake try to filter as much as possible, and then only the remaining will be sent to wavefront algorithm, and you can see how much speed up you would get even with variable length of sequences. With short reads and with long reads as well, you still maintain very high speed up. And that is the goal why we merge pre-alignment filtering with sequence alignment to accelerate the entire pipeline. That would be the key takeaway out of this paper. And just something to have a conclusion for this lecture, that most speed up you could see in any of those algorithms is coming from the parallelism enabled by novel architecture. Here we go over GPU and FPGA, which we're not going to cover in this course because we're not focusing on hardware, but also based on the algorithm. You cannot just have your own algorithm, which is performing very bad on CPU, and you just move it to the recent AI architecture or recent GPU or recent FPGA, and you expect your algorithm to perform really well. It doesn't work this way. You have really to take in mind the hardware that you are targeting, and then design something that is friendly with the hardware so that you can exploit the full power of the hardware that you are dealing with. And that is the best performance you would get if you target both sides, the software and the hardware all together. We discuss a lot, especially in this paper. So if you're interested in hardware, so I would recommend you to go over this paper to see much more discussion on the hardware side. If you are interested in software, I would recommend this paper first. And the second one is from molecules to genomic variation paper that we discussed in the first few lectures in the course. All right, that's it. That's the end for today. Next week, we will start going over advanced topic in read mapping with a paper called Genome on Diet. So Genome on Diet is a complete read mapper. So we have all the steps together in one topic. Okay. So we're going to cover that lectures, and then we will see how we move forward with the course. Okay. We have about 1 month. So we should be careful about writing the review paper. That is the right time to focus on it, try to finalize it, complete it. And then we will decide on the presentation slots for your paper, okay? But probably will be around end of April, early May. Remember, we have a deadline to submit the grade, so we have to present it before that. And probably it will overlap with your final exams from the other courses. So it's better to focus these 2-3 weeks on the paper writing. Try to finish it before you have a lot of final exams. Okay? We cannot extend the deadline. I'm flexible with the assignments, but not with the presentation. Yes, of course. It might be considered as a final exam, so we'll have one date decided, or we can have it as last 2 weeks in April, before the class ends. Okay, I think I have the exact date on the table of content. In the syllabus, you would see that the table of content, and you can see where we estimate the presentation would be, in which week exactly. But we can have some flexibility within that range, okay? But I really need your help to finalize the review paper, finish everything over there. You will start receiving feedback based on the draft you submitted. So I'll start sending you some stuff on things that you are missing from the review paper, things that you should include, things that you should focus on. So you could recap or try to fix all those issues within this month. Remember, we released assignment number 3. You have 7 days to complete it. After 1 week, I will release assignment number 4. And you could have 2 weeks to finish both of them, or you finish the first one within this week and then the second one next week, okay? But I cannot extend beyond those 2 weeks. Otherwise, it will be a problem with the review paper, okay? I expect around 4 pages, 4 to 7. That would be the optimal. You can go with more. I have no issue with that. I wouldn't deduct grades for having more things to explain, especially if you have figures, nice figure explaining how the algorithm works. Yeah, but I wouldn't expect less than 4 as well, right? Please focus on the critical analysis, the critiques. Don't explain too much on the introduction. Like, what is the history of this field? What is the history of those algorithms and so on? Yes, having a little bit background, it's always useful to give the perspective to set the stage before you start. But what I want to focus on the algorithm, how it works, how it compared with other algorithms, especially if you read 4 papers, right? And you are going to compare them together. What are the pros, cons of those tools, right? Similar to the analysis that we did in the lecture. So we see a lot of algorithms, and then I'm telling you that this is the best in terms of that, and that is the best in terms of this, okay? One important point, please do not use ChatGPT or any of the Gen AI, okay? Doesn't matter the tool you use, shouldn't use that. Otherwise, you will lose the benefit or the goal of why we have review paper, okay? Yes. Yeah, you could copy, but please give it a bit of sense of personality, okay? Based on reading the 4 papers. Is that true? Okay. Is what they claim is really true? What if the other papers say also something different? They contradict each other. It's okay to copy from the paper, and I'm always doing that, right? I copy from the paper, but you should give your own perspective, your own context, saying that, okay, this is what they claim, and I'm not sure if this is correct or not. However, in the other paper, in the experimental evaluation, they show that this is not true. They perform not really well with this particular data set, right? This is what I'm looking for. Your own perspective, your own context, your own point of view. What do you think about those 4 papers? Which one is best? Why this is not performing well? Why this is not working well? It could be related to the algorithm, could be related to the data set. They use something wrong with the data set, right? So this is really what I'm looking for in the presentation, right? Not summarizing the paper. That is not review paper. Summarizing the paper or just dropping the PDF to one of the Gen AI tool and then get some text out of it, that's not review paper. Please don't do that, right? Yeah. Thank you so much. We'll see you next week.